Hi, my name is Malek Nawes with Supelec France.
Hi, I am Hadi Noureddin with Supelec France.
Hi, my name is Quentin Baudinier with Supelec France. Welcome to the IEEE Online GreenComm 2014 conference. In this demo, we are going to present our Wi-Fi based platform for energy saving in wireless networks.
The constant evolution of information and communications technologies brings to end users new features and services never expected in the past. However, it also brings new challenges and technological issues to overcome. One of these issues is the quick growth of energy consumption in the ICT infrastructures. These infrastructures today are about 3% of worldwide energy consumptions and about 2% of worldwide greenhouse gases emissions. More than 50% of this energy consumption comes from the radio access networks.
For all these reasons, we focused in the context of this demo on the base station level. The main objective of this demo is to provide tools for rapid prototyping of next generation energy efficient and energy saving algorithms on the radio access network. Therefore, even though our target is cellular networks, we decided in this demo to emulate it with a WLAN network in order to be able to use unlicensed frequency and inexpensive equipments. The platform we proposed is depicted on the figure. As you can see, it's pretty simple. There is a central server which takes care of all the processing, that can manage a WLAN switch, which is in charge of managing all the different base stations or access points of the network. Let's focus a bit more on the platform. As you can see on this slide, the server we developed collects general information on the network. For every user equipment of the network, it is able to collect RSS measurements, delays, bandwidth, etc. It would have been possible to collect these measurements directly at the server, at the switch. But this would have forced us to deal with proprietary software, which we didn't have time for. Therefore, the solution we decided to implement is the opposite one. Every user equipment of the network, either Android mobile phones or personal computers on Linux, collects the required measurements and sends them via TCP sockets towards the central server where they are processed. As you can imagine, such an infrastructure is able to support a lot of 5G related applications. On the context of this demo, we focused on two of them. The first one is topology management or cell shaping, which means that we developed algorithms that can, while ensuring the cover of the network, turn off some unused base station, unnecessary base station, and therefore save energy. The second application we focused on this demo is the detection of devices clusters. Devices clustering basically consists of detecting groups of geographically close users. Our main hypothesis is that This info can be used in many of the 5G scenarios to save energy, such as beamforming and massive MIMO, or device-to-device communication, or deployment of heterogeneous network. In this demo, we show some cluster detection algorithms and we show the performance.
Let's start with the first application, dynamic access point switching on and off. The main idea is to minimize the network's energy consumption by dynamically switching on and off some access points when their traffic load is low, and then serve their connected users by the neighboring active access points. In this work, we recast our topology management problem as an optimization problem, where the object is to maximize the number of access points to be switched off under constraints, which are basically the user equipments can connect to only one access point, and the number of user equipment connected to an access point should be less than a threshold to guarantee a given quality of service. The main used metric of this algorithm is based on RSS matrix, which is composed by RSS measurements in dBm between one access point and a user equipment. In this video, we see live RSS measurements matrix in dBm where each row corresponds to one user equipment and each column to one access point. Then these measurements are averaged over a short time window and outlying values are eliminated. To show how our algorithm works, we present here a short demo of one access point switching off. It takes place at the third floor of Supelec Rennes campus building. At this floor, we deployed 4 access points that are always activated to avoid coverage black holes, and a small cell is deployed in a classroom and can be activated when needed. We show here a situation where 4 connected students are all leaving the room and going to the opposite side of the floor. So here the server can detect the event and switches off the small cell. This operation reduced the power consumption of the network by 3 Watt, which corresponds to the cell's idle state consumption. And now Hedi will present to you our second application, which is device cluster detection.
Clustering is the task of partitioning a dataset into several groups, called clusters, in such a way that the elements in the same cluster are more similar to each other than to those in other clusters. In the clustering problem considered here, the spatial proximity of user equipments, UEs, or devices will reflect their similarity. We define a cluster as a group of UEs having nearby positions, or in other words, lying in a small space area, as illustrated in this figure. One example of a cluster is a set of users inside a building or at a campus during working hours, inside a nearby houses, at a residential district, or at an event or gathering. We also define the clutter as the set of isolated devices. In other words, a cluttered device does not have other devices in its nearby vicinity. The appropriate densities for classifying UEs as clutter or cluster depend on the application that exploits clustering information and vary between indoor, urban, and suburban environments. We propose to use the RSS measurements to find the clusters without the need to know the locations of the UEs. RSS-based clustering is enabled by the fact that 2 nearby devices have a high probability of measuring close RSS values. To justify this point, we recall that an RSS measurement is affected by 3 major components of the wireless propagation channel, namely path loss, large-scale fading or shadowing due to obstacles, and small-scale fading due to multipath. Small-scale fading can be filtered out by averaging the signal over a time window or over the used bandwidth or by using multiple antennas. The path loss is a function of the distance between the device and the base station. The shadowing is commonly modeled as a realization of a spatially correlated random process with a correlation function decreasing with the separating distance between the two devices. Those nearby devices will experience close path loss and highly correlated shadowing, and will therefore have a high probability of observing close RSS values. The clustering operation starts by collecting the RSS measurements made with the UEs to a central processor and associating an RSS vector to every device, where an entry of this vector is obtained with one access point. We call this vector a data point. The figure on the bottom left shows an example of a matrix of RSS values. Each row of this matrix represents the RSS vector for one UE. Afterwards, a clustering algorithm is applied to the RSS vectors. The clustering solution should deal with the following problems. First, classifying the UEs as clutter or belonging to cluster. And second, finding the clusters for the non-clutter devices. The number of clusters is not known in advance and also needs to be estimated. We developed a non-parametric clustering solution to solve these problems. The application of this solution to the RSS matrix on the bottom left yields the results on the bottom right. In the following, we'll provide an example that describes how this solution works. In this example, the dimension of the data points is equal to 1. We can visually identify that we have two clusters represented by the squares and circles. Non-parametric clustering starts by placing a kernel function at every data point. Then, by computing the summation of these kernels, we obtain a non-parametric density function. The data points are assumed to be randomly generated according to this density function. To detect a clutter, we fix a threshold. Then we classify a data point as a clutter if the value of the density function is below the threshold. In this example, the 4 clutter data points are correctly detected. We mention here that the threshold value and the bandwidth of the kernel function should be carefully chosen. The number of clusters is defined to be equal to the number of modes above the threshold. These modes are determined by applying an iterative hill climbing process initiated at every cluster data point. The data point conversion to the same mode are assigned to the same cluster. Now we show some results of the application of this solution. The total number of UEs is 12. Here, clusters are well detected when their density is about 13 UEs per 100 meters square.
Now we present some experimental results about the performance of classifying user equipments as clutter or belonging to clusters. We define the probability of detection as the probability of correctly classifying a cluster user equipment and the probability of false alarm as the probability of wrongly classifying a clutter user equipment as belonging to cluster. The variable parameters are the number of access points, the clutter and cluster densities, and the number of clusters. This figure shows the variation of probability of false alarm, where we can notice that it increases with clutter density and decreases with the number of access points. The second figure shows the variation of probability of detection, where we can notice that it improves with the number of access points, cluster size, and density. In this demo, we proposed a Wi-Fi based platform for testing energy-saving algorithm for WLAN and cellular networks in real radio environment. The presented platform is tested with 2 application scenarios: dynamic access points switching on and off, and cluster detection for green radio applications. For both applications, we got encouraging results, and we will focus in the future in developing more advanced algorithms and extending our platform to other green radio applications. Thank you for watching.